we're going to talk about attitude estimation or attitude determination. And this is important because if you're on a spacecraft, right, you want to know what's my attitude with respect to some inertial frame. That's what we're getting at. And using a combination of both sensors and models to do that. You could break this up into two areas. So the first one would be, we'll call that static attitude determination. The static means that all the measurements are taken at the same time. We'll get to what these measurements are, but the measurement could be, where's the sun? What's the magnetic field? Where's the horizon? Where are particular stars? So these are all going to be based on sensors on board the craft that are fixed in the body fixed frame. And so they're determining a unit vector pointing to certain things that then can also be compared with what the inertial frame measurement is. If all the measurements are taken at a single time, you use this single snapshot in time to come up with some way of optimally solving for the geometry of the measurements to figure out what your orientation is. The goal is to get or estimate that 3x3 matrix, the direction cosine matrix that relates your B frame to some N frame. And the N frame might be the Earth-centered inertial frame. So there's static attitude determination, and that's what we'll talk about. There's something that's more complicated called dynamic attitude determination. And this is something where measurements are taken over time, and it's a harder problem. And why is it a harder problem? Because the measurements are taken over time, along with some gyro or rotation rate measurements. So we're taking sensor data, instantaneous sensor data, or maybe sensor data from different sensors taken at different times, along with some gyro measurements, like the things that are in your phones. So this would be giving a rotation rate. And then they need to be optimally blended together. And by optimally, we mean we're trying to reduce the error as much as possible. So that would get us into things that we're not going to talk about here, but you've probably heard of the Kalman filter, or maybe you've even used it. We won't be talking about that. So we'll focus on this static attitude determination. So the basic idea, we have a combination of sensors and also mathematical models. This generates data, and then an algorithm estimates the attitude by combining these. So the sensors, they measure unit vectors. I'll call those V, and there may be multiple ones, but we'll measure unit vectors that are in a body fixed frame. So we're taking a measurement with respect to a body fixed frame. So if this is my, here's my blue frame, body fixed frame. According to the spacecraft, I'm taking some measurement of something. Maybe it's where the sun's located. So I've got a vector pointing to the sun, and I know where that is in my body fixed frame. The mathematical model would be, if I know where I am in my orbit, I should be able to estimate to very good precision where the sun should be pointed with respect to that inertial frame. So that means, the other team, if you're working on a team, who's doing the orbit estimation needs to be getting it right. And that's where the mathematical model comes in. So we're also measuring, gives the same, and maybe to just emphasize that this is a unit vector, same vector, but in the inertial frame. And then we can combine these because they should be related. The vector in the body fixed frame should be related to the vector in the inertial frame by the direction cosine matrix, the rotation matrix. So this is the unknown that we're solving for. What are some typical vectors used? We turn them into unit vectors because that's all we care about. So we only care about directions. So the typical unit vectors that are used would be the sun vector, the magnetic field vector. There's like particularly bright stars that are known and what the star pattern around it is, the vector to a particular distant star. There's also Earth horizon detectors, and maybe we could think of others. But the algorithm boils down to trying to solve this for that unknown matrix. Okay. And at this point, it might be useful to think of, ignore the 3D world. Just think of, you're in your car maybe I'm in the rover. No, not the rover, because Mars has like either no or a weak magnetic field. Oh no, spoiler alert. So if I'm in my car and I want to find out what my orientation is, so this would just be the what's the 2D attitude determination. If I'm in I'll just make it like this. This is a car. I know the heading of my car. I've got some body fixed frame for my car, right? So B1, B2. How do I figure out what the orientation is? How many measurements do I need? I really only need to measure one known vector. So that vector, the one that you might think of, if you're out lost in the woods and you want to know what direction to go or what direction you're heading, if you have a compass, right, the compass will tell you what direction you're going. There's a compass. You take a measurement with your compass. So there's a known direction called north that's known in the inertial frame. And so we may as well call that the N2 direction, and then east is N1. So if on board, I've got a compass, let me do a little compass, and it's pointing, right? Compasses usually have the red side pointing that way and the other side. So it's telling me roughly where north is. Then I know my heading. I know my orientation. I could figure out my angle, and then all is good. Okay, this is where north is. I have my angle, theta. So we can determine theta, and from theta, you could get the rotation matrix. So there we are. So there is a question for the compass. Would the poles be considered singularities? Well, so for 2D, there's no singularities. If you were to do something like the Euler angle, there's only one angle, and theta dot is just equal to omega, if that's what you're talking about. Right now, we're just talking about attitude estimation. If our car happened to be pointing north, there wouldn't be any problems, or opposite north, there wouldn't be any problems. The main thing here is all we need to do is from the car, we have some known measurement. If I were to write it in terms of what I wrote up here as V, there'd be some vector V in the body direction. And I also know what that vector V is in the inertial direction. And then I could compare those two. So I know that VB is BN, VN. Of course, because this is just a 2x2 matrix, it becomes easier to solve. It gets trickier when we're talking about 3D. Why is it trickier? How many measurements do I have to make? So if this is my rigid body, kind of arbitrarily oriented in three-dimensional space, and then here's my inertial frame, how many measurements do I have to make? How many unit direction vectors are required here? You need more than one, I'll tell you that. So let's suppose we know where the sun is. Here's the sun. And we have a vector pointing towards the sun. I'll call that S hat. And that's measured in the body frame. But we've got very good orbit determination. So we also know what direction that should be in the inertial frame. With only one measurement, we cannot sense rotations about that axis. So to actually fix the complete 3x3 rotation matrix, we need a second direction. So you need more than just one. So that might be worth saying. With one vector measurement, you don't know if you're rotated about it. You can't sense rotations about that single measurement. So you need a second vector that's not collinear. So if I had another, say, sun sensor and it's pointing at the sun again, well, that doesn't help me. I need to sense some other direction. So a common other direction might be the magnetic field. Maybe I'll write that as M hat, depending on where I am in my orbit. So to determine the attitude, we assume we already know the inertial direction of certain objects, like the sun, the earth, the magnetic field direction, the stars, maybe the moon. Yeah, we already know the inertial direction of certain objects, right? And the magnetic field changes as you go around the earth. So you need to know where you are in your orbit. We know where stars are, the moon, etc. For explaining, I'm just going to focus on the sun and the magnetic field. And I think I have an illustration I can show you. It might make this a little bit easier. All right, so here is a little schematic showing we got our satellite right there, and we've got a sun sensor on it. So if the sun sensor senses the direction of the sun, that gives us, we know S hat, and we're measuring it in both with respect to the body fixed frame, so the satellite fixed frame, and also since we know where we are in our orbit, we know which way the sun should be pointed. Let's say we have a magnetometer on board that's sensing the magnetic field. So here's the local magnetic field. And if we have a good model of what the magnetic field should be at that location in our orbit, then we're good to go. With sensors, we would get S hat in the body fixed frame and also the magnetic field in the body fixed frame. And from the model, based on where we are in our orbit, we know where the sun should be in the inertial frame and where the magnetic field should be pointing. Remember, these are unit vectors. So that means we can then relate them. And so we'll use the information from these two equations to try to find Bn. So I'll talk about a couple of methods to do that. First, though, let me say a little bit about these sensors. We'll start with the sun sensor. So the sun is pretty easy to see, right? So that's what's nice about a sun sensor. So what does the sun sensor do? A sun sensor might be made up of multiple individual sensors, but at the end of it all, we want to provide the unit vector to the sun in the body fixed frame. That's what we're going to want. And it's used by virtually all spacecraft, partly because many of them are powered by solar panels. So you want to orient the solar panels to point towards the sun as directly toward the sun as possible. And you might want to point sensitive instruments away from the sun. Let's say this is I don't know if the Hubble Space Telescope has ever stared at the sun, but I think it's bad for it like it is for us. So to point sensitive instruments away. It's a relatively simple instrument, and there's a few different types. I'm going to mention just one, and it's a photocell. So here's an example, the photocell. It's a photocell. It generates a current proportional to the amount of incident light. So just to give you a schematic, here is the photocell. This is in a known orientation on our spacecraft. So maybe I'll call that, hopefully it's not confusing, but N hat. This is it's the normal to the photocell. And then we've got the sun somewhere, let's say over here. Here's my sun with all of its rays. And light is coming in from the sun. Right, it's hitting the photocell from the direction of the sun. So what we're getting is, if I were to write the unit vector for the direction of the sun, S hat, it generates a current proportional to the incident sunlight. This angle between the two, we'll call that alpha. That's an alpha. And so the amount of current at an angle alpha is equal to the amount of current you would get if it was directly overhead times cosine alpha. S dotted with N is cosine alpha. So there's a question, is the sun sensor primarily good for coarse attitude determination? It's actually one of the most precise directions that we can get. So I'll later list a table of sort of the accuracy of various sensors, but this one is very good. You need more than one photocell. Why is that? Because the sun, if we were to do this at an angle, kind of think of the photocell at some kind of angle. In fact, I think I have a picture of a photocell just so you could get an idea. Like, they're not the prettiest things in the world. So here's a photocell. If I were to do the unit normal, just sort of plot it on here. Here's my unit normal. And if I know that angle, well, I actually don't know the other direction. So the sun could be in any kind of cone. If you want, I'll try to make a cone of directions. That's not the best cone in the world, but I don't necessarily know exactly where it is. So from the one angle, alpha, this defines a cone around n hat. So I don't know exactly where the sun is. And this is the key thing. With one photocell, sun vector could be anywhere along this cone. The way that you resolve the actual sun direction is you have multiple photocells. So resolve the actual direction with photocells oriented in different directions. So if the sun is really here, and on my spacecraft, I've got a photocell with a unit normal, all this tells me is that, well, could be anywhere in this cone. If I have another photocell, this diagram might get complicated. If I have another photocell oriented in a different direction, then that will give me another cone. And these two cones will generically intersect in two lines. So that's with two photocells. With a third photocell, now I can pick up the three cones will intersect in only one line. The cones intersect in two lines. You might be thinking, why aren't they just, touching? Well, that's if we assume that our two normals just happen to be in the plane of the sun vector. But you got to think of, no, they may not be. So that means there's two possible directions it could be. So a third photocell, three cones intersect in one line. And then that would be giving us what we want, S hat in the body fixed direction. And in practice, multiple photocells are used for redundancy, and they're all over the spacecraft, right? Because we don't know exactly which side the sun's going to be on. And some you could do and come up with an algorithm to figure out exactly which way the sun's pointing. So many photocells for redundancy and all over spacecraft. The advantage is that these sun sensors are sort of the standard in terms of accuracy. They can provide 0.01 degree accuracy, which means it's very good. It's very good. And they're usable anywhere because you can see the sun anywhere, meaning even large orbits, large altitude orbits. So that's a sun sensor. There's other kinds of sun sensors too. There's cheap ones that just sort of, they give a step function response like, am I pointing at the sun or not? They don't give kind of information on an angle. And some of the times those are used to just activate hardware. So maybe you've heard of a sun presence sensor. There's also magnetometers. I think I've got a picture of one. Here's one. I just sort of looked up a company that sold magnetometers. Looks like it's, orient this with the Z direction that way and then XY over here on the side. So what does this do? It's not really pointing anywhere. It's just it's like a 3D compass, right? It measures the magnetic field direction and it's in the body fixed frame. So we'll call that M hat B. You can compare that with a mathematical model of what the magnetic field direction should be at that point in our orbit. And that gives you M sub n. So what does that mean? Model based on where we are in our orbit with respect to Earth's magnetic field gives M. That same magnetic field direction, but in the inertial frame. I've got some pictures of the magnetic field. Right, if you haven't seen the Earth's magnetic field, there's the geographic North Pole. That's the pole at which we're rotating around. If you didn't know it, the magnetic North Pole isn't exactly aligned. It's the magnetic North Pole is somewhere in Canada, but we have a model of where it is. So you could figure out if we knew what our orbit was doing with respect to this field, then we would know at each point what the magnetic field direction should be. Yeah, this is kind of cool too. This is just showing, at different spots in the orbit, this is the way that the compass would be pointing. The compass, in this case, would be the magnetometer pointing in the magnetic field direction. So if we have an orbit that's like equatorial, then almost always the magnetic field will be pointing in that one kind of inertial direction. You might be saying, what inertial frame are we using? Well, here's a couple of frames. We could either use like the Earth-centered, Earth-fixed. That's a rotating frame though. So there's the Earth-centered inertial, where you could either use the ecliptic as the plane, or you could use the equator as the plane. So for satellites close to the Earth, we probably are using this one, Earth-centered inertial equatorial as the inertial frame. And this is a cool video. I think you get it. If we know where we are, then we get that measured. And the same thing for the sun. The sun, when we're near Earth, the sun's, I guess it depends on like what's the day. So you need to know the time precisely to know, okay, where is the sun? Where's the Earth in its orbit compared to that inertial frame? So where's the sun? And then you get SN from the model. But this is just to give you an idea of at least for those two things. The problem with the magnetometer, I guess the good thing is they're reliable, they're lightweight, they're low power. They could work well in a wide range of temperatures. They're kind of bad in that they're only usable when the magnetic field is strong. So I'm just going to list their drawbacks. Only useful below about a 6,000 kilometer altitude. Right, the Earth's magnetic field diminishes as you get further away. They're also, they're not too accurate. And for multiple things, the Earth's magnetic field kind of changes, so our model is wrong. And also the instrument's accuracy could be wrong. So they're not too accurate. And it sort of depends on where you are. You might think, oh, at lower altitudes, these are going to be great, but they're not. There's sort of like a sweet spot of the highest accuracy. So at 200 kilometer altitude, we're talking about near the ISS and stuff, they have a 5-degree accuracy. So that's not very good. At 5,000 altitude, they have about a 1-degree accuracy. And just compare with the sun sensor, right? The sun sensor was 0.01 degrees, so at least 100 times more accurate. So the sun direction is going to be the most accurately known in general. There's other sensors, and I'll just put in here a table of the sensor accuracy. So we got magnetometers. There's other things listed here as well. Earth sensors, like it might be at some point you might, there are things that are able to detect the horizon of the Earth. Those are getting pretty accurate too. Star sensors, I guess, are the most accurate. 2 arc seconds, that's much, much smaller than a degree. Gyroscopes have this accuracy, but that's related to more the dynamic attitude sensing. You'll have to know more once you actually design a spacecraft and the attitude sensing. This class is more focused on the basics and the theory, but hopefully this gives you an idea so you can work from this. So we're now going to go into the attitude determination algorithms. Okay, so we'll suppose that we can make at least a couple of measurements. Maybe one's more accurate than the other. And then how do we use that to determine things? Right, you might, I show multiple sensors here. You might actually have multiple known vectors or measured vectors. And we're talking unit vectors. So maybe v hat 1, v hat 2, v hat 3, and so on. I don't know, you might have a lot. We're going to, just for now, to simplify things, assume that all we have is a sun sensor and a magnetic field sensor. So we're going to have a sun direction and a magnetic field direction. Just like I had before, we know S in the body fixed frame, and we also know S in the end frame. And we also know the magnetic field in the body fixed frame and the magnetic field in the end frame. And then we want to construct that direction cosine matrix. So how do we do that? There's 2 methods we'll go over. The first one is called the TRIAD method. It's not necessarily the most accurate, but it is popular and it works. So the first method is called the TRIAD, and often capitalized. And the idea here is that to determine the B frame related to the N frame, we first introduce a third frame, and maybe I'll do lowercase triad, the triad or T frame. Let me sketch out what's going on. So if we have a body fixed frame, there's going to be a lot of unit vectors here. So here's B1, B2, B3. That's our body fixed frame. It's some frame attached to the spacecraft. There's also the inertial frame, like the Earth-centered inertial equatorial, something like that. And I'll do that in red, like I've usually done things. So here's N1, N2, N3. We need to pick one of our measured vectors as the first direction for a third frame. And I'll make this third frame green. Here's what we do. We assume, or we assign this T frame is going to be, T1, T2, T3. Write it that way. So we're going to assign T1 equals the sun direction. So if the sun direction is, say, over here, and that's measured in, or we know it in both frames, we call that T1. Now, we're trying to create a right-handed coordinate system. The magnetic field, right, could be pointing somewhere else. We're not going to say T2 equals M. And why not? Because those two aren't necessarily perpendicular. So we need to construct a second unit vector for this T frame that it's going to be perpendicular to create a right-handed coordinate system. So here's what we do. We say that T2 is equal to S cross M, because S cross M definitely has to be perpendicular. And I don't know what direction that's pointing. It's over here. And we have to normalize this because S cross M isn't necessarily a unit vector. So it's S cross M divided by magnitude of S cross M, the norm of S cross M. So that gives us a second vector for this frame. For the third direction, T3, that's just given by T1 cross T2. And that'll complete the right-handed coordinate system. Seems like it should be pointing maybe over yonder. Right, it's hard to get an idea in 3D, but hopefully you're getting the procedure. If possible, I would animate this and rotate it. So we've got the sun direction and the magnetic field direction, and we use them both. We're primarily using the sun direction. For the first thing that you assign, you want the most accurate vector you have. And just based on our description here, the sun vector will be known with more accuracy than the magnetic field. So it's almost like we're using all of the information about the sun vector and then kind of half of the information about the magnetic field direction. And then we construct these unit vectors. And we know what these unit vectors are in both the B and the S frame. So we know what this T1, T2, T3 in both the B and N frames. In terms of the B and N frame components, I'll do them, the body fixed and then inertial over here. So you could see them side by side. We know that, T1 in the body fixed frame is S in the body fixed frame. Same with the inertial. T1 in the N frame is equal to S in the inertial frame. And then T2 in the body fixed frame will be S cross M divided by the magnitude of S cross M in the body fixed frame. Same over here for T2N, but with inertial frame components. And we'll go through an example of this so you could see. And then number 3 in the body fixed frame is just T1 in the body fixed frame cross T2 written in the body fixed frame. Same thing over here. This is T1 N cross T2 N, right? So we're making a right-handed triad of unit vectors. So this is the body fixed triad unit vectors, and this is the inertial triad frame unit vectors. Now, in the absence of measurement errors, both sets of these triad frame representations should be the same. But of course, there will be error. We're going to say we will estimate the body fixed frame with respect to the end frame, and we'll refer to that as B bar. It's our estimate. We can write the rotation matrices, the direction cosine matrices, as this B hat, so the estimated body fixed frame with respect to the triad frame. If you remember how we write these, what you could do here is you write these vectors as column vectors, and those populate the 3 columns. And just to remind us of that, I'll write it this way, T1B, and that's a column vector. So I'll just put dot, 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 dot. That just reminds us this is a column vector. So it means the first entry is the B1, second entry is B2, third entry is B3. Okay. And then the second column, as you could probably guess, be T2B. And then the third column, T3B. So we construct it as columns. And we could also construct how the inertial frame relates to the triad frame. And we're writing it this way, NT, so that we could, again, just write what we've got over here as our inertial triad unit vectors, again, as column vectors. So this is T1N hat, written as a column vector, T2N hat, column vector, T2. Like these aren't ones, these are just dots to remind us it's a column vector. T3N. There we go. So we've populated 2 3x3 matrices. Then we can finally compute the desired rotation matrix. So this is the end of the algorithm. This is the estimated rotation matrix, direction cosine matrix. B, we'll say B hat N. And right, what is B hat N? This is going to be BT, the way we've learned it would be, times Tn. But Tn is just the transpose. So you could write it that way. So that means you take the first matrix you've written up there, and then you multiply it by the transpose of this second matrix that you've written. And that's it. That's the estimate. If we knew the true rotation, then we could figure out the accuracy. But all we have is an estimate. So we'll look now at an example, a numerical example, to go through this, where we actually know what the true rotation matrix is, and then we could estimate what our error was. So before we do the example, are there questions about this? The bar over the B means it's estimated. It's not the true. B bar means estimated. Just so that we remind ourselves there's always measurement error. So let's do a MATLAB demo. So here I will use some commands from that zip file that had all of the algorithms, the MATLAB algorithms contained in the book. So I'm going to be following example 3.15 in the book. And so you could try this as well. We're going to try the triad algorithm. We're going to assume that the true spacecraft body frame, the attitude relative to the inertial frame is described by a yaw pitch and roll of 30, 20, and negative 10 degrees. So maybe I'll just write that this way. Yaw pitch roll equals 30, 20, negative 10. And remember, this has to be written into radians for me to use it in any reasonable way. So we could either look up in the back of the book or, in one of the earlier lectures, or I already have over here this Euler 3212C. It came from that zip file that has a whole bunch of routines. So I'll just use that 3212C of yaw pitch roll. And I get that matrix. So this would be like, this is the true rotation matrix, which we would not have access to if we were estimating things. So now we're going to assume that just to make life easy, we're going to assume that the sun direction in the inertial frame is actually just pointing in the x direction. So this is 1, 0, 0. And I'm going to do everything as column vectors. So if you don't know, that little quote thing means transpose. And then I'll assume, just to make things easier, that the magnetic field is in the z direction, the inertial z direction. The true body fixed direction of the sun is going to be something like Bn times, not something like, exactly this. So if I do this, what do I get? I get that. That's true. I'm going to introduce a little bit of error because there's always going to be some error. I'm going to introduce an error of about 1.5 degrees. So instead of using that as my SB, I'll say that with error, this is going to be something else. And if we were doing this carefully, we'd like do it more carefully. Like say, oh, there's some random error of so many degrees, but this is just an example. So, you know, I notice I've taken and slightly changed some of those entries. And this isn't necessarily unit normal. So I do have to do SB equals SB divided by norm SB. That'll make sure it's normalized. And what's the magnetic field? Magnetic field true is Bn times Mn. I'm going to introduce a little bit of error to that. Maybe make it a little larger since it is the magnetic field. Make it about 2 degrees. So I've already figured out what do I need to do to make it 2 degrees? Because again, I'm just doing a demo. 38 negative 0.1548, 0.9362. So it's slightly different, right? And again, I have to normalize this just to be sure. That's unit normal. So these are going to be off. You're like, well, okay, they're slightly off, but gives an idea of the lack of accuracy. So now what's the triad method? The triad method is we construct T1, T2, TB, the T frame unit vectors in both the B frame and the N frame. So we're going to use the sun as our first vector because we're assuming that's the more accurate one. So T1B, maybe you want me to move this up or something? I don't know. T1B is SB, good enough. T2B, the way that you do cross products in MATLAB is you write the word cross. So this is cross SB, MB, and then we do need to normalize, so the norm of this. And then T3B would be the cross product of T1B, T2B. We don't have to normalize because T1 and T2 are already orthogonal and normal. So there we go. And then you could, I don't know if it's instructive to see what those matrices look like. Might be like, okay, what is T1B? All right, it's that. And then you have the others too. And then T2B, it's that, T3B. Remember, what does this mean? This means the first component is the B1 component, then the B2, and then the B3. So I guess at this point, if we wanted to, we could construct the bar BT matrix, right? I'm not calling it BT, I'm bar because it's estimated. And since we've already written these as column vectors, it's really easy to write it in MATLAB, T1B, T2B, T3B. Voila, there it is. That's just going from B to T. So now we have to do the same thing for all the others, but in the N frame. So there's that. T2. Let's change everything to N. 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 Okay, and then T3N is cross T1N, T1N. N and B are next to each other on the keyboard, which is going to lead to problems. I don't like that. Okay, there we go. We can construct N, the entity matrix, just like we said we would. T1N, T2N, T3N. So now we will write the estimated rotation matrix. So this is bar BN equals bar BT times NT transpose. So that looks okay. If we want to know what the accuracy is, we have the true BN, and we could sort of look at the entries, but we could actually get what how far off we are in terms of the axis and angle formulation. How far off are we in terms of the angle of rotation? That's a good measure. So the angle would be 0 if this was correct. The way that we get that is we go from the estimated frame, bar B, to B. And what is that? That is bar BN times BN transpose. Now, if this was perfect, we would have ones along the diagonal. This would be the 3x3 identity matrix. Now, how can we compare? How do we find out how good this is? Well, we could use that phi. So I'll call it error phi, the number of degrees. Arc cosine 0.5 times the trace of bar BB minus 1 times 180 divided by pi. Do I have all my parentheses? There we go. Okay, so we're off by 1.8, 1.9 degrees. And that error comes from the error that we baked in by putting in error for the sun vector and the magnetic field vector. So that's good. So I basically worked through, despite there was some kind of hiccup there, I was working through example 3.15 that's in the book. And you could try it as well. So what we'll talk about more when we discuss this subject again is other methods, right? This just used 2 vectors. But if we go back to that issue of what if we have more than 2? So if we have n observations of unit vectors, so maybe we've got more than just the sun, the magnetic field, the stars, then how do we estimate the best attitude matrix? So for all of them, right, we've got V1, V2, all the way to Vn, measured in both the body fixed frame, and then we know it in the inertial frame. So for each of these, there'd be V1b equals estimated B and V. No, I don't want to put a 1. I actually want to put an index there, K, V, K, N. And K goes from 1 to little n, because we've got n observations. Our goal is to find this estimated matrix. We want to find the best estimate. And we could do that in a least squares sense. This is called Wahba's problem, after a statistician who's still active. Her name's Grace Wahba. She came up with the solution she wrote the problem and the solution. What we do is come up with a cost function. So we want to minimize a cost function. We'll have to talk about the solution next time when we get to this, but the cost function, it's a cost function for getting the best estimate of this matrix, and I'll use J. This is 1/2. K goes from 1 to n. We could put weights on each of these measurements, but we're writing V hat K in the body fixed frame minus BN, right? If you were to rewrite this and just make it something equal to 0, right, that would be equal to 0. We're doing it now, running it this way. So we want this to be minimized. If measurements were perfect, then J equals 0. But we're not necessarily going to have measurements perfect. So what this does is it minimizing that cost function gets the best estimate for this rotation in a least squares sense. So you've probably seen cost functions in a control class, and they're often like quadratic. And then what's this factor of 2 for? There's going to be something that happens where the factor of 2 goes away. So that's why the factor of 2. The different weightings would be, you would weight higher, more accurate measurements than less accurate measurements. So you've probably seen things where there's, X and Y, and you've got some data points and they're sort of scattered. You want to get the best estimate curve fit in the least square sense, meaning this is the least square line, minimizes the sum of the distance squared to data points. So we'll look at the solution to that, or one solution, next time. And the main one we'll use, because it can be written particularly nice in terms of the Euler parameters or quaternions, and that's called Davenport's Q method. Q because it's going to be based on quaternions. All right. So that's it. I'll sign off and see you later.